Okay, let's get started. We have a huge agenda today. And we are going to talk about vector fields. And actually, we are now entering the last part of the course. Up till now, we have, here in springtime, we have considered integration in the plane and in space along a curve. And now we're going to use it in order to look at fields, vector fields. And the agenda is, I'm going to introduce you to the tangential curve integral. And in doing so, I'm also going to talk about the gradient vector field. Then I'm going to talk about indefinite integrals of vector fields, in vector fields. And then I will discuss another subject, flows. And we'll look at flow curves. And we will look at flow surfaces. These subjects here are linked to the exercises this afternoon. Let me write this down. This is the gradient vector field is exercise. Let me write that. Exercise 3 plus 4. And then indefinite integrals is in 5 plus 6 plus 7. And then finally the flow curves is 1 plus 2. So it's in a different order, but that should be transparent when you look at it. So let's now define what is a vector field. Let's talk about a vector field in the plane. And this means that to every point x, y, we attach a vector. That is, if we have this point here, then we write it in this way here. We have like this. So you have coordinate functions that are functions of two variables, v1 and v2, and this is a vector. This is a vector symbol, and normally for vector fields you use capital letters. So let me also introduce a vector field in space. And here you have to every point x, y, z. We attach a vector like this. You have this vector field here is a function of x, y, and z. And you have the three coordinate functions, v1, v2, and these are, each of them are, say, real functions, the real functions of the three space variables. So this is how it looks. And normally when you have these two things here, when we look at this, we normally think of a force field that is at each point there's a force operating, and it's doing something to a particle or what have you. Here you look at the vector field typically as the velocity, but is now you're given the vector field and you have a velocity in each point, and then if you put a particle in this velocity field, you want to know where it moves about in this vector field. So it's two different tasks that we are going to look at, but let's start with an example. And here I am looking at a plane vector field, and it looks like this. The first coordinate function is x times y, and the second coordinate function is y plus 1. You have your xy plane here, and let's say that this is 1, this is also 1, so let's look at these 3 points. Then you can compute the vector field, or you can compute the vectors in these points. For instance, in this point, this is 1, 0, this is 1, minus 1, and this is 1, 1. So you simply plug in the x and y values in this vector field here, so you get that if you plug in this point here, you get 1 times 0, that is 0, and then you get 1 plus 1, that is 2. No? Sorry? Y is 0, so 1 plus 0 is 1. And the normal thing you do when you are looking at vector fields, that is you plot it or draw it from the point where you have calculated the vector field. So I draw here the value of the vector field in that point. Now if we take 1, minus 1, that is this point here, you get 1 times minus 1, that is minus 1, and then you get minus 1 plus 1, that is 0. So in this point here, you have this vector. And finally, here you have the vector 1 or 1 plus 2. So it'll be a vector like this at this point. But the heart of it is that every point in the plane has a vector attached to it. So you can go to any point in this plane, and then you can draw the vector from this this expression here. Now, a special vector field that we're going to discuss is the gradient vector field. And we have here, we're given a function of the three variables here, x squared minus y plus z. And then you can construct this vector field, namely the gradient of f. The gradient of f is simply the derivatives in three directions, x, y, and z. So the first coordinate here is the derivative of this function with respect to x. You get 2x, you have to keep these constant, so you get 2x. The derivative with respect to y becomes the second coordinate, and then with respect to z, the third coordinate. So this is the gradient of this function here. Now, this is the easy part. That is, if you have given a function, it's very easy to compute the gradient of that function. But what if you're given a vector field? Is this a gradient of a certain function? Can you actually calculate a function that will yield the vector field when you take the gradient? So let's try that out. And let's try it with this vector field we started with. So we assume that this vector here, x times y, y plus 1, is a gradient field. The correct thing is to say gradient vector field. Often you just say a gradient field. Well, if this is the case, then a function f exists such that the derivative of f with respect to x is equal to x times y, and the derivative of f with respect to y is 1 or y plus 1. If f exists, then it should fulfill these two equations. But then you can do what we call a cross-check, because if you take the derivative of this with respect to y, and the derivative of this with respect to x, then they should be equal. We've seen that. For continuous functions, these two, or the order of differentiation doesn't matter. So we have that xy, and if you take the derivative of this one with respect to y, you should keep x constant, so you simply get x, and you get f. If you differentiate with this with respect to x, you get 0. And clearly they are different. So you cannot find an f such that these two equations are fulfilled. So it is not every vector field that is a gradient field. But we will find out how to actually find the function f if it is a gradient field. In order to do so, we need to use what is called the tangential curve integral. We start out with the simple case where V is a constant vector field. That is, to every point in, let's just take the plane here. It could also be in space, but at every point here, there is, you can attach this constant vector here. So you could draw it here, or you could draw it here, you could draw it everywhere. So this is the case. Now, what I'm going to use an analogy from physics, because I'm going to talk about the work that this vector field performs on a particle. And say we have a particle here, and we move it the distance delta u, and we move it in the direction of this. Now the analogy is that this is a force field. So then V is said to be doing the work, the numerical value of V times this motion here. So this is the work. This is only the situation here where we have this constant vector field. What if we have that V is just a continuous vector field? That is, we have, say we have a curve here, like this. And then we have, say, our vector field like this in this point here. This point, say we have a parametric representation of this curve. And normally we call that R. So this point here, say, is the value of this parametric representation. So you are at that point. Then, say if you pass some times, and then you have moved the particle delta nu along this line here. Then we define define the work. I just introduce here a unit vector along the tangent of the curve. So we define E is a unit vector in the direction of the motion. Then we look at the resulting force in the direction of the motion. In this case here, the resulting force will be the projection of this vector or this force here on the tangent. So I write here is equal to the resulting force in the direction of motion. Like this. Now, if the motion is very small, that is, then we say that V has on the small segment of the curve, it has done the work namely the resultant force, or the universal value of that, times this BU. And this will be the projection, this resulting force here, will be the projection of the force field, or V, on the tangent vector, or not the tangent vector, the unit vector, in the direction of the motion. And then this should be du. And now you can sum up all these small contributions to the total work. And then we say that V has along the curve K. Did I write that? No, I did not. This is the curve K. It has done the work K, and this is this projection here times this. And what you can see here, what you can recognize here, is that this is a curvilinear integral that we have discussed previously. So now you can resolve this integral in for the parametric representation. So let me repeat here, we parametrize K with this parametric representation, and you have some unit or some limits to U. It goes from A to B, and this from the first point to the second point, or initial point to the final point. Then we can interpret this one, this integral here. This should be the dot product. Because this will be the integral from A to B, and then you have to take the restriction of the vector field to the curve K. And you do this by putting in the parametric representation in K, like this. Fine, not in K. And of course, in your vector field. Sorry. And then this should be guided by a unit vector in the direction of the motion. And let me just, I have it here. You see, the direction of motion is in the direction of the tangent, let's say, to the curve K. So this will be the tangent vector to the curve. And if you want to get a unit vector, you just divide by the length of this tangent vector. So you get r prime, and then divided by the length of this. And now you have to remember something. Is when I'm going to resolve this curvilinear integral into this parametric representation, what should I remember? What is it that you should remember whatever you do when you do curve integral? You said it, the Jacobi. The Jacobi function, and the Jacobi function for this curvilinear integral is simply the length of the tangent vector. So we arrive at this tangential curve integral. And we have our parameter, or we have our vector function times this unit vector, and then this differential here. And you see this cancels with this one. So we have this simple formula. We have this restriction of the vector field to the parametric curve, and then got it with the tangent vector. This is it. This is nice and simple. I just want to give you a short example here. So let me take this here. I have this vector field here, y minus x. And then I have a circle. That is, I have this parametric representation. Pick this up. Cosine u sine u. So we are on a circle. So let me draw the circle. Like this. And you see here, let's say this point is 1, 0, so that will be 0, minus 1. So this is the value of the vector field at that point. At this point here, you have x is 0 and y is 1, so you have this vector here, and so forth. Here you have x is equal to minus 1, so that will be this vector here, and then like this. And let's then compute the value of because within an integral you have to then make the restriction of the vector field to your curve. And this is simply to put in the functions. Instead of y, you use sine u. Instead of x, you use cosine u. And then you have to dot it with the tangent vector. The tangent vector is simply the derivative of this parametric representation here. So you get minus sine u, and then you get cosine u, and then you have your dq. So this is the value of this integral, and this is easily computed because when you do the dot product, you get sine u times minus sine u, so that is sine squared of u. And here you get minus cosine times cosine, so that is minus cosine squared of u. I can put the minus sign outside, and here I just get a plus 1. So this is equal to the minus the integral from 0 to 2 pi of 1 times u. So that will be u taking between these limits, and you get the value minus 2 pi. So it's negative. The work can be negative. And this is, of course, because the motion is in that direction. The force field is always opposite to the motion. So this is why the work becomes negative. Okay, let's take a break, say for 10 minutes. I need to clear the blackboards. Thank you.